Hello dear students. So in today's class I am going to start a new series, and that series is the molecular orbital theory. And in this particular lecture series I will be discussing this molecular orbital theory in the pretty much detail, starting from the linear combinations of atomic orbitals, and then I'll extend this particular theory to the diatomic molecules, homonuclear diatomic molecules, as well as heteronuclear diatomic molecules. And later on in the series I'll also give a more detailed concepts of the molecular orbital theory applied to the polyatomic molecules like water molecule, carbon dioxide, methane, etc., ammonia, right? So this is my lecture number 1. Please remember, this is my lecture number 1 of the molecular orbital theory. And in this particular lecture today, I will discuss the linear combinations of atomic orbitals, which forms the basis of the molecular orbital theory, right? But the question is that what is the need of the linear combinations of atomic orbitals? Why it is important to adapt such approximation? Okay, so for this, this is your Schrodinger wave equation, right? This is time independent Schrodinger wave equation, and this is a very general equation, and it is very easy to achieve this particular result when you apply the basics of the quantum mechanics on the quantum chemistry on the particle in the one dimension box, right? So solving this particular Schrodinger wave equation for the multi-electron system is extremely challenging, right? And due to several reasons, making it practically impossible to obtain the exact solutions, right? So first of all, you should remember that if you have, say, this Schrodinger wave equation, then it is quite simple, and this equation is solvable for the simple system. Simple system means like, see, particle in a box, whether in a particle in 3D box. Say this is the equation for the particle in the 3D box, right? And it is also simple. This equation, this Schrodinger wave equation, is also simple and solvable for the systems, hydrogen-like systems, or the hydrogen systems where only one electron is under the influence of the one nucleus, right? But this wave equation, Schrodinger wave equation, for polyelectronic systems, right, where you have the multiple electrons, right, it is quite challenging to solve this particular equation without adapting some kinds of the approximations, right? So various of the approximations are there, say like your variation method is there, your perturbation method is there, then again your Born-Oppenheimer approximation is there, and then your linear combinations of atomic orbitals is there. So I'll discuss the linear combinations of atomic orbitals. I hope this give you the little deep insight why actually it is important or necessary to adopt the linear combination of atomic orbitals method, right? So here is some of the complexity. If you want, then you can remember this thing, right? See, when you increase the dimensionality, right, that means for n electrons, when the number of electrons increases, poly-electron system occurs, then the wave functions depends on the 3n spatial coordinates, right? Here, 3 coordinates x, y, and z is there only for only one electron, but when you have the n electron system, then these wave function will depend on the 3n spatial coordinates, right, and n spin coordinates as well, which leads to an exponentially growing complexity mathematically. So we cannot solve this particular equation, wave equation, for the complex system. Second thing is electron-electron interactions, right? Repulsive interactions between the electrons. This introduce non-separable terms in the Hamiltonian, which complicate the solution further. We will not get the exact solution, right? See, this is the partial differentiation equation, right? And in this partial differentiation equation, it is very necessary to get the exact solutions. But when you have the electronic repulsion, then the exact solution we cannot get. That's why it is making more challenging to solve this particular equation for the polyelectronic systems. Then non-linear equations. The nature of the equation is the non-linear, and multi-electron systems involve non-linear differential equations which resist to the analytical solutions. That means we cannot get the analytical solution, that means the exact solution. So these are the some of the mathematical challenges as well. Apart from this, your physical challenges are also there, then your computational challenges are also there. So we need to adopt the linear combination of atomic orbitals method, right? So here you see I have written the linear combination of atomic orbitals, right? And this linear combination of atomic orbitals basically originated in the early days of the quantum mechanics, right? So when the quantum mechanics was started in its early days, then this linear combination of atomic orbitals was adopted, right? And John Leonard Jones, he introduced the linear combination of atomic orbitals for the diatomic molecules in 1928. And based on this John Leonard Jones concept of linear combination of atomic orbitals, then Charles Colson applied this particular LCO linear combination of atomic orbitals method for the polyatomic molecules in the 1929. And after that, Robert Mulliken and the other scientists, along with the Robert Mulliken, developed the molecular orbital theory in the 1930s. So these 3 years are very, very important, 1928, 1929 and 1930 for the your molecular orbital theory, or for the development of the molecular orbital theory, right? So what is the linear combination of atomic orbitals? See, for this you need to know, say for example, I am having this H2 molecule. Simply I can write this H2 molecule, and you know how we can form this H2 molecule? Hydrogen atom, say I am calling this hydrogen atom as Ha, and another hydrogen which is bonded with this one, I am calling it as Hb. But remember, this Ha and Hb only I am taking to explain the certain things. However, these two are perfectly identical, and the linear combination of atomic orbitals holds good only for the diatomic molecules where both the atoms are exactly same. But when they are the heteronucleotides, then these linear combination of atomic orbitals shows the variations or the fluctuations, right? And you know, see, in the light of the de Broglie equation, what de Broglie equation says, the wave and the wave particle duality, right? So that means we can treat particle as the electron as the particle as well as the wave. But in the linear combination of atomic orbital, we will take the electron as the wave. Please remember, we will take the electron as the wave, right? And in the light of the quantum mechanics, you know, when you have the wave, then definitely the wave function would be there. And I will call this wave function as the psi. Okay. And for hydrogen Ha, I'll call the wave function of this particular atom, hydrogen, psi A, right? And for the hydrogen of the second kind, which is the Hb, I will call this wave function as the psi b, right? Now, what will happen in that case? You know, see, when I take this electron as the wave, so I can treat like that. So this is the sine wave, right? And the quantum mechanics student knows that. And this electron wave is basically, it's a sine wave, right? And you know, this is the crest, right? And this is the troughs. Okay, and say this is the wave function psi A, and simultaneously you will have another wave function of the identical kind for the second kind of the hydrogen atom, which I'll call as psi B. So what is the linear combination of the atomic orbital? Linear combination, we can get the linear combination by adding or subtracting these two wave functions together. This is known as the wave interference, right? So here I am explaining how we can form. Say for example, there are different ways by which we can combine these two wave functions, right? So first of all, say I'm writing, if I want, say, okay, let me take the stylus first, right? Say this is my psi. This is the wave function of the molecular orbital. This psi is the wave function of the molecular orbital. Please remember, this is wave function of molecular orbital, right? Wave function. And that wave function I can get either by adding these two wave functions of the hydrogen atoms or by subtracting them. So I'll get one kind of the wave function of the molecular orbital when I add these two, And then I'll get the another kind of the wave function for the molecular orbital when I subtract these two, right? This is something very, very important which you need to know. Now, suppose you can see here, I'm first of all, I am adding these two together, say psi, and I am adding these two wave functions, psi A plus psi B, okay? And I'm calling it as B, where B stands for the bonding molecular orbital. In the linear combinations of the atomic orbitals, when we add the two wave functions, then it forms your bonding molecular orbital. So this is the wave function of the bonding molecular orbital. So this I have shown you here. Say this positive side actually shows that the positive phases or the positive sides of these two orbitals actually overlapping together, right? So this positive side actually indicates this positive as well as this positive. This indicates the same phases are overlapping together. So this will overlap like that only. So this is the whole molecular orbital, right? This one, the wave function for this one. Sorry, for this one wave function, right? This is the wave function, which is the solid line. And if you see carefully, then these are the individual wave functions of the atoms in them. When we add these together, this is known as the constructive interference. In the constructive interference, what is the meaning of the constructive interference? If I have this particular wave, right, and I lift this particular wave function and try to superimpose onto this one, so what will happen? The crest of this particular psi A will be overlapped by the wave function of the psi B. So this is known as the constructive interference, where the phase angle would be the 0, cos phi. Phase angle means your cos phi. Cos phi would be your 0. When the phase angle is 0, then these two reinforces each other and the magnitude increases, which I have shown you here. See, this is the wave function which is going this one, psi B, and you see this is the psi A, and this is overlapping with this one. When this happens, actually what will happen? This amplitude increases, right? This amplitude increases. Please remember, right? So this is where one nucleus and one electron in the periphery. This is one nucleus and another electron in the periphery, and we are adding these two together and forming this molecular orbital. So you can see here, this is the nucleus and this is another nucleus. And in between these two nucleus, there is increased electron density. And I have shown this increased density by the dark blue color here. So dark blue color is representing that in between these two nuclei, electron density is quite large. When the electron density here is large, that means this electron density will shield this nucleus from the repulsion of this particular nucleus. So the nucleus repulsion increases in that case, and attraction between the electron and the nucleus increases, right? Which gives the greater stability to the molecule. That's why it is known as your bonding molecular orbital. There is high electron density at the center, and this is low electron density at the corners, which I have shown you here, right? So if you want to get the electron density, and it is important to get the electron density in order to understand the importance of the energies of the molecular orbitals, right? Which will form. So what will happen? See, in the light of the quantum chemistry, probability density or the electron density is given by the square of this, right? And when I do the square of this, then I'll do the square of this as well. Okay. And when you apply the simple mathematics on it, right? A plus B whole square, then A square plus B square plus 2AB. So you will have your psi A square, right? And then you are having psi B square, and then plus 2 psi A and psi B. This is very, very important. This psi A square is the probability density or the electron density in the hydrogen atom A, which is this particular one. Okay. And this psi B square is the electron charge density in the atom type of the B. And when I'll have this thing, then when I combine these two, I'll form the molecular orbital. And this is the increased charge electron density, and that increased value is basically this one, 2 psi A and psi B. It is very, very important to understand. This is very, very important. Without understanding this, it is almost impossible to understand the linear combinations of the atomic orbitals. So you can see here what I have explained you so far. Your psi A square and psi B square, this indicates the electron charge densities of the wave functions in the in the atom, hydrogen atom A and the hydrogen atom B, that is psi A and psi B for the isolated atoms, right? And this psi B square, basically, this psi B square, this represents the wave function of this bonding molecular orbital, and this is the, when I do the square of this one, this is the electron charge density between the atomic nuclei. And higher, see, higher the value of this psi B, higher would be the interaction and greater the stability of the molecule. And you can see here, this psi B square basically is this psi B square. If I write like that, this psi B square is basically greater than this psi A square and psi B square by a factor of 2 psi A and psi B, and that 2 psi A and psi B is basically the increased charge density between the two nuclei. Please remember this one, right? So this term actually results from the interactions of the orbital of the overlap of the atomic orbitals, right? Higher the, larger the overlapping of the atomic orbitals, greater would be the charge density between the nuclei and more stable the bond between the two atoms. It is very, very important to understand. Now, if I plot this charge density, right? This charge density along with this, the your electron densities of the individual atoms, right? So here this is electron charge density, and if you want, then you can write this psi B of the square. This is the electron charge density, right? And here you can see this solid line. This solid line represents what is it? It is representing, it is the electron charge density of this hydrogen atom A, and this is the electron charge density of the hydrogen atom B, and this blue area is representing the electron charge density of this particular molecular orbital. Now you can see here, see, earlier one, your electron density was present here only, and electron density was present here only, but where I linearly combined them by adding these two wave functions together, so I am resulting this extra part, right? This part is the extra, which is what? 2 psi A psi B, right? This is 2 psi A psi B, which is actually the square of this, the bonding molecular orbital, this one. This is very, very important to understand. This is constructive interference of the wave. If you want, then you can write constructive interference. So I am writing here constructive interference. Constructive interference of the waves, right? Now moving to the next slide. Now here I am showing you the destructive interference. So what, for the destructive interference, what I can get here? I am having psi, this one, and I am putting asterisk or the star over there, right? See, please remember, for the beginners, it is very, very important to understand, whenever the B is written over there on the wave function sin psi, then this represents the bonding molecular orbital, right? And whenever you find this asterisk or the star, this represents the anti-bonding molecular orbital. So what happens when we combine linearly these two atomic orbitals? My second way of combining them is what? My psi A will combine with this like that. That is psi B, right? This is how I can get. So this is the this is your wave function for the anti-bonding molecular orbital. This is the wave function of the hydrogen atom A. This is the wave function of the hydrogen atom B. So if I show you, so how I can actually draw the waves like that only. Say this is my one wave. For example, this is, say, my psi A. Now my psi b, because I am subtracting these two, right? So here I am put minus here. So what is the meaning of the minus here? The positive side of psi a will overlap with the negative side of the psi b, or vice versa. Positive of psi b can interact with the negative of the psi a. So here you see, this is where psi a positive part and this is the negative part, and I am combining these two. And when I combine these two, and then I have to cross this nodal plane. So this is your nodal plane. So I'm writing here, I can write here, this is the nodal plane. This is here, nodal plane. Okay, this is your nodal plane. So when I combine this to this, that means I have to cross this particular nodal plane, and this will produce extra node in the molecular orbital. And you know, node is the volume where the probability of finding the electron is 0. So say, let's say my second wave is coming like that. This is my second wave. This is destructive interference. Please remember, this is destructive interference. So I'll try to write more clearly in that here only, interference, because earlier slide I wrote very casually, right? So this is destructive interference. Here you can see this phase angle, right? This phase angle is actually 180 degree. So here your cos phi is 180 degree. But in the earlier case, here, see like that here. In this case, so I'll use the red pen for this one. Here your cos phi was 0 degree. Please remember, okay? However, I am not including that much of mathematics here. So it is enough to say that the phase angle is 0 and the phase angle is here 180 degree in the destructive interference. There is no need to write this cos phi and other things, right? But if you want, then you can write. This is destructive interference. So now what is happening actually? This positive sine wave is actually combining with the negative sine wave. And here I am crossing the node for this one. So my net result would be like that. I'll find the node in my molecular orbital, and node is that particular volume where the probability of finding the electron is 0. Okay. So here what will happen? See, this is the wave function, this is the wave function. And what will happen when this phase angle of 180 degree would be there? Then the amplitude basically decreases. Amplitude decreases. That means earlier when I was having the more volume for the electrons. Now, but after combining in the destructive interference way, now I am having the less volume for the electrons. That means bond is not very, very strong, and it is of high energy, and it will give the instability to the molecule. And I have shown this here. You see, this is the psi A. So if you want that, I can write here. This is my psi A, and this is my psi B, and this one is my psi star. Okay. So here I have shown you, or rather you can see the psi A square, psi B square, or here psi steris square, right? So here you can see electron charge density is quite less between the two nuclei. However, the electron density is very, very high at the periphery of the two nucleus. So here both these two nucleus are exposed along with in front of each other, and there would be the increased repulsion because electron density is less. There is no screening of these two nuclei. So these two positively charged nucleus will repel each other, and you know the repulsion increases the energy of the system. So the resulting molecular orbital will have the high energy, and this would be your anti-bonding molecular orbital. I hope this is quite understandable to you. Now, if I want to plot this one, right? So here you see this solid line. This solid line is the wave electron charge density square, because I have written the square here. That means electron charge density, right? So this is the electron charge density of individual hydrogen atom A. This is the electron charge density of the individual hydrogen atom B. So again and again, say I am repeating this electron charge density in the hydrogen atom. Why I am calling it hydrogen atom? Because hydrogen atom is the simplest one. That's why I am taking this particular example. However, all these things are true for the all kinds of the homonuclear diatomic molecules, whether you are taking C2, B2, N2, O2, F2, etc. This is true for everyone, right? Now, when I combine these two, right, by the destructive interference, so for destructive interference, what I will do, I'll make the square of this one, and again I'll make the square of this one. Then this will give you what? Psi A square plus psi B square minus 2 psi A psi B. That means my psi star square is less than less than psi A and psi B by a factor of minus 2 psi A psi B. See, in the earlier one, in the previous slide, what was happening? This actually psi B square actually is greater than the psi A and the psi B by a factor of plus 2 psi A psi B. But in that case, when the destructive interference is occurring, this psi star square is basically less than from this psi A and psi B by a factor of minus 2 psi A psi B. So when this happens, actually, you see this blue, you can follow this dashed blue line. This is combining. And when the different phases, positive and the negative phases are overlapping, we are crossing the nodal plane. So here we are having the node. That means electron density is quite poor here, or the very low or the zero electron density is there. So here you are having the node, right? So electron is not there. So this increases the energy of the system, which gives the anti-bonding molecular orbital. So this is simply your linear combinations of atomic orbitals. This is quite important, right? And the distance between psi A and psi B, this is basically your bond length or the bond distance. So I haven't written here actually because I have downloaded this particular pictures from the internet. So this is actually not only distance, it is bond distance. See, in the earlier picture as well, not in the next, but in the earlier picture as well, it is your bond distance, or you can say the bond length, right? So this is your linear combination of your atomic orbitals. Now, there are certain things which you need to understand, right? See, for the very effective overlap, see, if you want to overlap two atomic orbitals, it is very, very important. Certain conditions must be met. First of all, the combining atomic orbitals must have the comparable energies, right? When they have the comparable energies, only then they can. In case of the homonuclear diatomic molecules, they must have either comparable or the same energies, right? But for the heteronuclear molecules, you can combine the orbitals of the different energies as well, because in the heteronuclear molecular orbitals, right, or in the heteronuclear molecules, what will happen? Higher electronegative atom actually will have the lower energy of the molecular orbitals. This I will explain you when I will explain the molecular orbital diagram of your oxygen molecule, right? So it is very, very important. The energy of the atomic orbitals combining together must be similar in magnitude, right? Or their atomic orbitals should have the comparable energies, right? In case of the formation of the homonuclear diatomic molecules like your H2, N2, F2, B2, C2, etc., right? So this their linear combination of atomic orbitals holds quite good, right? So this is known as the linear combination of atomic orbitals. So another one, see, symmetry criteria is also there, but symmetry criteria I'll explain when I will form the pi and the sigma bonds, right? So this is something very, very important which you need to understand. Now you can see here, if I move further, so here is the complete picture. This is the atomic orbital, right? Psi B, and this is the atomic orbital of psi A, or you can write psi A on the left hand side or psi B on the right hand side. This will not make any difference. This is the energy which is going up. Since we didn't take any scale, so we can write not to the scale. It is very important for the science students when you are plotting any graph without actually defining the scale. So it is mandatory to write not to the scale over there, right? This will give, this will give your evaluator a good idea that the student have a good knowledge of how to plot the graph, etc. Right? Now I am combining these two. So first of all, I am adding together. That means psi A plus psi B, and this will form the psi bonding molecular orbital, psi square plus psi B square plus 2 psi A psi B. And due to this increased electron density between the two nuclei, you know the attraction, this molecule is quite stable, right? Because these nucleus are actually screened by the electrons, so their energy is low. So this low energy molecular orbital, see why this low in energy? Because this energy is lower than the psi A and the psi B, and when they have the low energy, this is known as the bonding molecular orbital. These are the two nuclei over there. And another molecular orbital which will have the higher energy than the combining atomic orbitals, which is known as the anti-bonding molecular orbital, right? So for anti-bonding molecular orbital, it is quite important to write here psi star. This is very important to write the psi star. Okay, so this is psi B, this is a psi star. Okay, so I cannot write psi A for this one because this is the anti-bonding, right? So this is the molecular, this is the linear combination of the atomic orbital, right? And then if I go further, what is the difference? See, I have drawn this bonding molecular orbital here and this anti-bonding molecular orbital here. Now, what is the difference between the two? So first of all, bonding molecular orbitals, BMOs, I am calling them. BMOs are formed by the addition overlap, that is the constructive interference of the atomic orbitals, while ABMOs, anti-bonding molecular orbitals, are formed by the subtraction overlap, which is the destructive interference of the atomic orbitals. The second one is the wave function of the bonding molecular orbital is given by the psi B square of this one, and this will give you the psi A plus psi B whole square, and this will further give you what? This will further give you, so okay, I am not able to write on this particular picture due to certain regions. Okay. So, this I have explained to you how we can explain these things, right? Psi square, psi B square plus 2 psi A, psi B. And here, minus sign is there, the wave functions of the anti-bonding molecular orbitals, right? Or electron charge density, not the wave function actually, the electron charge density. I should write the electron charge density of the BMOs is given by this formula, and the electron charge density of the anti-bonding molecular orbitals is given by this particular formula. So, you please write the electron charge density instead of the wave functions, right? So, bonding molecular orbitals are formed by the lobes of the overlapping of the orbitals having the same sign, that means positive or overlapping. Anti-bonding molecular orbitals are formed by the lobes of the overlapping of the orbitals having opposite sign, plus and minus, which I have explained by earlier slides. Bonding molecular orbitals have lower energy than the combining atomic orbitals, as you have seen here. Bonding molecular orbitals have lower energy than the combining atomic orbitals, and anti-bonding molecular orbitals have the higher energy than the combining atomic orbitals. Please remember this one. This will form the basis of the molecular orbital theory. In the bonding molecular orbitals, the electron charge density is high in the region between the two nuclei, as I have shown you here. Electron charge density in the bonding molecular orbital would be very, very high between the two nuclei, and the electron charge density in the anti-bonding molecular orbital would be less than the between the nuclei of the two combining atoms, right? And the last one, every electron in the bonding molecular orbital stabilizes the molecule, and every electron in the anti-bonding molecular orbital destabilizes the molecule. See, whenever you are deciding the stability of the two atoms or the ions, right? So you can count the electrons in the bonding and the anti-bonding molecular orbitals. Higher the number of the electrons in the BMOs will stabilize the molecule higher, and higher the electrons, higher the presence of the electrons in the anti-bonding molecular orbital will destabilize the molecule, right? So this is all about here linear combination of atomic orbitals, and in the next class I'll explain you the molecular orbital theory for the diatomic molecules. I hope you understand the lecture. You understood the lecture quite well. If you understood the lecture, please give the thumbs up to the lecture. And if you are new here watching video for the first time, please subscribe the Tetrahedron Chemistry classes and do share with your friends as well, right? So that's it for today. Thank you very much.